like with a lot of these complex videos that I put together, there are always a few things that don't quite fit in the makeup of the discussion. But they are still topics that are of note. So real quick here, I did want to point out that there are settings that allow you to reverse the input, do an input hold state. You can input debouncing. I mean, there are a whole lot of different settings in here that you can set, averaging the calculation for the analog input, etc. The one thing I wanted to note in regards to just the pulse width modulation is you can change the frequency output for the first four and the last four ports. You can also do some dithering to try and even out the variation or the chattering or anything that you might be seeing in the pulse width modulation signal. The thing that I can show us in this video here is kind of just the difference between the frequency out that you'd see if X1.3 set for 200 hertz and the other channels here I set for 100 hertz. And we're going to be looking across X1 in particular and X4. So now if I pull up the oscilloscope and with these settings, take a look. Now you'll see that there's an overlap here, but you'll see that the duty cycle of each one of these is the same. It's just they're offset by that 100 hertz. So now if I change this here, and let's say I want to make this, let's make it 50 hertz and write to device. There we go. We just need to expand out there a little bit. Okay, now there's both the same 50% duty cycle, but now we can see the offset here in the oscilloscope. So just another nice little visual that I can give you to show you a little bit of the difference in the signal using the oscilloscope. The dithering, I tried playing around with that a little bit. That's really not something that really pops out in the oscilloscope when I tested it here. So at any rate, hopefully that gives us a little more insight into what you can do with the pulse width modulation output. Thank you, and have a good rest of your day.